Okay, for our day 2 on polar curves, we're going to talk about area. And just as we could find the area of a function on a certain interval from A to B, and that's what our first picture is right here. We can see that we would deal with rectangles, of course. We would have the width or the base of the rectangle would be delta x. The height would be f of x. And we could integrate from a to b of f of x. Our dx, of course, would be equivalent to delta x. We would be able to determine the area bounded by the function and the x-axis. Well, we're going to do the same basic principle, find area enclosed by polar curves. Instead of working with rectangles, we're going to instead work with sectors. First of all, just a little comparison. When it came to functions, we generally were working with the x comma y coordinate. X would be our independent variable. We would start there, and then we would have our output of y. Y depended on x. Here with polar curves, we're going to have the polar coordinate of r comma theta. Really what's a little unfortunate is theta comes second as the second coordinate, but it's actually where we would begin. So we would envision a theta. If r is positive, we would go that distance out from the pole. If r is negative, we would be projected backwards. But what I want to immediately make a comparison for is, with x being our independent variable, theta being our independent variable, we had our width of a rectangle with x, delta x. Here we would have delta theta. And delta theta is, of course, going to form this sector that we are forming here. So from geometry, we have the area of a sector is 1/2 r squared theta. And that is only true if theta is in radians. So just making this direct comparison, if we would have a d theta or a delta theta, you could envision a little sector being formed here, and this picture shows that rather nicely. Using this formula, we could find that the area differential, dA, would be 1/2 r squared d theta. Well, what we really need to know is this formula here. That area of a sector shows up as we integrate. Really, we could turn this into a Riemann sum, just as we had done with rectangles. But the area of a region between the origin and the curve r equals f of theta, for theta between alpha and beta, we'll have alpha to beta 1/2 r squared d theta. Of course, r will be written as some function of theta. So very, very, very quickly, what we could do is take a look at example 1. Find the area of the region in the plane enclosed by r equals 2, 1 plus cosine of theta. Now we could plot this out by hand. We could plug in theta equals 0, theta equals pi over 3, and so forth. And for any given starting angle theta, we could then move r units away from the pole, from the origin. But what I'm going to do right now is actually get some help from the calculator, just trying to speed through this. Go to y equals, let's clear this out, and type in very quickly 2, 1 plus the cosine of theta. And by the way, use this type of thinking. Cosine could get as large as 1. 1 plus 1 is 2, and 2 times 2 is 4. So the largest our r could be would be a 4. So I'm going to have our theta min, pressing window. I'm going to go between 0 and 2 pi. We might need to adjust that. And like I said, the largest our r could be would be a 4. So for x min and for x max, I'm going to be typing in negative 4.5 and positive 4.5. Just give a little bit of extra space in there. And again, let's just double check that our mode is on radians. It is. When you hit graph, you can see that we get this type of a curve. This is called a cardioid. And the cardioid, of course, looks something like a heart. And so we could see very quickly that our shape looks something akin to this. Now, I think it's very, very important for us to talk about the angle boundaries. The angle boundaries are so very important. Something that can be very, very helpful is to say, hey, is this really being completely graphed between 0 and 2 pi? You might wonder what happens if we just graphed from 0 to pi itself. And if we were to graph that, you could see, in fact, that we're only graphing half of that cardioid. So this becomes an issue later on, because sometimes a curve is completely graphed, not between 0 and 2 pi, but between maybe something else, such as between 0 and pi. Why is that so important? Well, if we're going to find the area, we need to know the angle boundaries that are plotting that curve out in its entirety. That's between 0 and 2 pi. So I'm going to say 1/2 r squared. And just to help you out real quickly, even though we could work this out by hand, we could expand all of this, I think it would be more helpful if we used fn_int. And speaking of that, my goodness, we have a wonderful tool here. If we just go to the home screen, we could hit math and come down to fn_int. Now, it's very possible that students don't have this latest version of the calculator, in which you would have things looking a little bit different. But regardless, when you type in fn_int, instead of typing in 1/2 and then that 2 times 1 plus cosine of theta quantity squared, rather than having to retype that, look at the vars key. The vars key is a few buttons, 3 buttons above 9. I'm going to press vars, go to y vars, go down to polar, and just type in R1. And then, of course, we have to square that. Come over here and type in a theta. And then, my goodness, all we have to do, hitting enter, we will see it's 18.849 or about 18.850. Using AP rounding, either answer would be correct. One more quick comment. Very often our answers will have a pi in them. If you wanted to see what would happen if we just divided out a pi, you'd see that we'd have 6. So really, if you wanted an exact answer, you'd be at 6 pi. Okay, so from here, let's very quickly take a look at this other issue of number 2, finding the area inside the smaller loop of the limmason, r equals 2 cosine of theta plus 1. Well, again, let's bring this up very quickly, clear this out. We'll say 2 cosine of theta, and then, of course, we can say plus 1. Now, again, cosine can be as large as 1, so the r value would be maximized at 3. 2 times 1 is 2, 2 plus 1 is 3. So what I'd like to do, again, let's keep this between 0 and 2 pi just to get us started. And then, just as I said, it's between 3 for our largest radius. So I'm going to just change negative 3.5 and 3.5 for our x-min and max to the same for our y's. We know that we cannot have a larger or a greater distance of 3 with our r. So when we hit graph, you get this limmason, and of course, a limmason is going to look something like a cardioid, but with a inner loop inside of it. And this inner loop is exactly what we're being asked to find. Well, this can get to be a little bit more of an issue, of course, as we're envisioning our graph being made, and then we have our inner loop here. The big question is, my goodness, what are the angle parameters, the angle boundaries for our loop? And here's something that can be very, very helpful. Look, as you're asked to find a loop specifically around the origin, what you'd like to envision is that your r would be 0 when you begin the loop and when you'd end the loop. So take your r value and set r equal to 0. If you did that, we could subtract a 1, then divide by 2. You'd see that the cosine of theta would equal -1/2. Well, it doesn't take too much to see if we're going between 0 and 2 pi that, let's see, all students take calculus. You know cosine would be negative in the second and third quadrants. So we'd have 2 pi over 3 and 4 pi over 3, where our r would equal 0. Well, why don't we try this? Have your window, instead of beginning at 0, why don't we begin at 2 pi all over 3? Similarly, let's go from 4 pi all over 3 and see what happens. If we were to graph this out, you would see that's exactly how we would arrive at our inner loop. So a little bit of algebraic solving that we'd have to do. Let's just say that we're going to go from 2 pi over 3 to 4 pi over 3. We'll have 1/2, and here's 2 cosine of theta plus 1 squared d theta. Again, we very quickly could let the calculator evaluate that area. Let's hit second enter again. And the wonderful thing about this is that the area of a polar curve is always 1/2 r squared. And you've stored your r in r1 now. So, tell you what, let's go down here and say I'm going to go from 2 pi all over 3. And up here we'll move up, oops, let's bring that back down to 4 pi all over 3. And with just one punch of a button here, we can find that our area of that inner loop is about 0.543. And I believe that we could also round it to 0.544 using AP rounding. Either of these answers would suffice. Now, something to be aware of, very often symmetry can show up. Let's just say that you were asked to find this formula, the integral that would represent the area of the smaller loop on a multiple choice test. And you frantically look and notice that this integral, which is correct, is not there. You know, is there another way that we could represent this area? And with symmetry, indeed, we can. Here's something that I'd like for you to notice. On the unit circle, if we were at 2 pi over 3 and 4 pi over 3, just looking at those two angles, directly in between them would be pi. So just want to point something out to you. If we were to graph, say from 2 pi over 3 up to pi, you would see that you'd only graph half of that inner loop. So using symmetry, we could say that this would be 2 times from 2 pi over 3 up to pi. And we could see that the 1/2 here would actually get crossed out with that 2. So I just want to point this out because sometimes symmetry shows up quite a bit, and it can be a little bit alarming to kids because as they're finding angle boundaries, they don't necessarily think of pi, but this would be an equivalent integral that would measure the area of that inner loop. Likewise, we could also have gone 2 times, well, how about we go from pi to 4 pi over 3? Just showing you that pi to 4 pi over 3 would also be half of that inner loop area. Something to keep in mind on a multiple choice test. This would be another form of that area. All right, well, coming back, I think we're going to need a little bit more time to finish the third problem. But just as we had in functions, we had a function f and a function g, we might be asked